All right, hi everybody. So today we're going to go over some practice problems in this last half of the chapter, and there's a couple of different examples. All of this is actually going to end up being your homework, so make sure you're watching through this video. So instead of like a formal homework set, you're going to do the practice problems from this, like we would have done in lecture in class. And so I'll make sure to point out each of those problems, but we're going to walk through the first one. So this first one asks you to calculate free energy change, so delta G, from delta H, T, and delta S. So we're going to use that very first equation we were given. We were given some information. We were given the formal equation. We were told delta H and delta S. We were also told the temperature is 298 Kelvin. So all of this is going to be pretty much plug and chug. Okay, remember that our initial equation that we were given in our chapter was delta G naught equals delta H naught minus T delta S naught. So we're just going to plug our values in and we're going to end up with 173.3 kilojoules. Now that delta G naught is positive. So what that tells us is that the reaction is not spontaneous under standard conditions, meaning given what we were told, this reaction will not occur in this forward direction. Instead, what we can take from that is that the reverse reaction, in fact, would be the spontaneous one. All right, so that means it's your turn. You're going to do this particular problem, and once you're done with the value, so you want to calculate delta G naught and tell me if the reaction is spontaneous or not under the conditions you were given. When you're done, you can go ahead and move forward. All right, our next problem is going to be calculating the standard free energy from the free energies of formation. So this is going to be like the appendix values. So this is going to be calculating delta G naught given some delta G values from our appendix. So first thing we have to do is get the values from the appendix. So we're going to go into our appendix C and we're going to find delta G of formation. So delta G naught F of P4, Cl2 in the gas phases, so make sure you're doing the right phases, and PCl3 gas. And what we're going to get is we're going to get these different values. So we're going to set it up so that delta G naught equals the sum of the coefficients times each of the delta G values in the products minus the sum of the coefficients times delta G of the reactants. So what that looks like is this one down here. So it says delta G, sorry, I'm going to try and move me, it's weird. Sorry. So what it says is that delta G is going to equal our 4, so the 4 for PCl3, which is in the balanced equation, times the value that we got from the back of the book, so the appendix. Then we're going to subtract that from the sum of the P4, so one of the reactants, plus the other reactants times 6. So it turns out that the delta G naught formation of Cl2 gas is 0. So 0 times 6 is 0. That's why you see the 0. Plus the 1 times the P4's value in the back of the book, also a positive value. So pay attention to the positives and negatives. And we're going to end up with a total of a negative 1100 kilojoules. Okay. And this is, of course, at the temperatures we were given. So we can only use this method if we're doing this reaction at 25 degrees Celsius. If we're at any other value, then what we can do is we can actually take that delta G naught that we calculate and plug it in to the delta G equals delta H minus T delta S. So we may have to do a different way of this. We may have to use the appendix to calculate delta S first, delta S naught, and then we may have to use it to calculate delta H naught, and then we plug all that in to get delta G naught. And again, we would use that method if we were not using a 298 Kelvin reaction. The second part of the question, B, says, what is delta G naught for the reverse of the reaction? So we're going to flip the reaction, and we're going to do the same calculation. So we're going to take those values and we're going to flip them around, and what we end up seeing is just the positive version of the one we just calculated. So we're going to get positive 1102.8 kilojoules. All right, your turn. You're going to use the delta G values at the back of the book to calculate delta G naught of the reaction for the reaction of methane gas, oxygen gas, carbon dioxide gas, and water in the gas form. Okay, when you're done, go ahead and move on. All right, next thing we're going to do is we're going to look at the effective temperature, so like we were just talking about. So the first thing we are going to do is to predict the direction in which delta G will go with increasing temperature, and then we're going to calculate delta G at two different temperatures. So for the first temperature, we can use the appendix method, and for the second temperature, we're going to have to use a longer method where we calculate delta H and delta S. All right, now let's look. So this one says that delta G equals delta H minus T delta S is going to be our best friend. That's like offset. It should be down here. And what we're going to do is we're going to actually answer part A by figuring out the sign of delta S first. So we can figure out delta S by a couple of different methods. One is to use the appendix values, which would be my favorite. And then once we know that, we can figure out delta H and delta S for the reaction using those appendix values as well. And once we have those, we can plug everything into delta G. So we have a couple of different things we have to do. All right, so first thing we're going to do in part A is we're going to go through and we're going to do the temperature dependence of delta G. So we're going to go to the back of the book and we're going to figure out what delta S is first. And in looking, we see that delta S is actually going to be negative. So then negative T delta S becomes positive, and the overall reaction is going to be not spontaneous, is what that sounds like, right? So delta S is negative, negative T delta S is positive, and increases with increasing temperature. So delta G becomes less negative or more positive, which means more non-spontaneous. Yes, that's correct. Okay. All right. So now for part B, we are going to use those values in the back of the book. Delta H naught is going to end up being negative 92.38 kilojoules. Prove yourself that by going into the back of the book and finding the delta H values for each of the individual reactants and the products, and then doing the products minus reactants for delta H. Do the same for delta S. You should get these two values. The book has just said, oh, we've already done this in previous practice exercises. We didn't do this 19.5 exercise, so at the very least, you should be able to do this delta S one. This is one of your homework problems from last week, or a similar version of it. So we're going to take those values and we're actually going to plug in our temperature at both of them. The first one they're going to do, they actually ended up just using this method, the appendix method, for both the 298 Kelvin and for the larger temperature, the 500 degrees Celsius. So for the first one at 298 Kelvin, they got a value for delta G naught of negative 33.3 kilojoules, which means a spontaneous reaction. And for the second one, where they did the larger value of the temperature, they got a positive 61 kilojoules. So make sure that you're looking at the right units. So your units should be in kilojoules. If you do math using the appendix for the delta S values, you need to convert those values to kilojoules by multiplying by 1/1000 for any of the delta S values that you plug in from the back of the book, because the back of the book has them in joules per Kelvin. We want to do everything in kilojoules because our delta H values are in kilojoules. All right. The next thing to do is to just kind of describe what happened. So at lower temperatures, this reaction is spontaneous. At higher temperatures, this is going to be non-spontaneous, and that's really all to take away. Next thing I want you to do is the same thing, but I want you to do it for two temperatures. I want you to do a different reaction. So it's this 2SO2 plus O2 makes 2SO3. And then what I want you to calculate first is using the appendix values to calculate delta H. Remember that method. It's from chapter 15. And for delta S naught, which is again from chapter 19, I believe it's actually 19.4 that you can use to help you do that one. And then once you have the values for delta H and delta S, you're just going to use delta G naught equals delta H minus T delta S for both A and B to calculate at two different temperatures. Please don't forget to use Kelvin for your temperature. I think you're actually given your values in Kelvin here. So yeah, when you are done, you can go ahead and you can move on. All right. So next thing that we're going to do is under non-standard conditions. So this is one of those last equations from our lecture. The first one that said delta G equals delta G naught minus RT ln Q. And also the K equals the E to the negative delta G over RT. Sorry, I'm just trying to memorize it. So at 298 Kelvin, so that's one thing, we know our temperature. We know the pressure values of each of these individual gases. Remember that pressures and concentrations can be used interchangeably in our Q equations or in our Q values, right? So in our Q's and K's, we can use pressures or we can use concentrations. So when we're calculating Q, I will remind you from chapter 16, 17, I don't remember off the top of my head. In trying to get our equilibrium expressions, remember that Q and K are the same, just that Q is done outside of equilibrium, K is done at equilibrium. So the way that we calculate it is the same. So we're going to take the products raised to their powers, which are going to come from our coefficients in front. And then we're going to plug that in, and we're going to plug our values that we were given in to find what Q is. Then we're going to take that value of Q and plug it into this equation that we're given for non-standard delta G. Remember, without the little naught, it's non-standard. With the little naught, it's under standard conditions. So one of the other things we have to do for this particular problem is we have to figure out what standard delta G would be for this reaction. Now, we've already done that. We did that in a previous problem, but if you don't remember that, you're going to want to go back and look at your answer from a previous problem. I believe that previous problem was this guy. Okay, at 25 degrees Celsius, we calculated what delta G naught was at 25 degrees Celsius. We said it was negative 33.3 kilojoules. Okay, back to where we were. So then we're going to take that delta G naught, and we're going to figure out how to use that to get our delta G standard. Okay, so next thing we're going to do is we're going to plug a chug. So we're going to take that negative 33.3 kilojoules per mole. We're going to add RT, ln, Q. We calculated Q. We know what R is. We know what T is. Now this term right here converts our joules into kilojoules. So don't forget to do that when you're doing this math. We are using kilojoules per mole in this chapter. Please make sure you convert or have something in there to convert. The R value has to be converted because it's given in joules per mole Kelvin. You'll also notice that this is not the same R value we've used in the past. Make sure you're using this one instead of the 0.08206 because 0.08206 doesn't have joules in it. Okay. From there, you're just finishing off the math. You get negative 44.9 kilojoules per mole. That means under non-standard conditions, this reaction is spontaneous, right? Remember, we're looking at those delta G values and we're interpreting them. We're not just saying, oh, it's negative blah, 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 or it's positive blah, blah, blah. We have to put a concept behind it. All right. Oh, sorry. Your practice exercises there at the bottom. It's the same reaction. So you're going to use the same delta G naught or the same standard delta G. You have the same temperature, so 298 Kelvin. So really the only thing that's changing here is what the Q is. So you need to plug these values into Q and then plug that into this equation. All right. Our next one is going to be our last one. So delta G, calculating delta G calculating the equilibrium constant. So this is using that K equation. K equals E to the negative delta G standard, delta G naught, over R times T. And we talked about how that got derived in the end of our lecture. Worry less about derivation and more about just plugging and using it, okay? Up here we're given delta G naught in joules per mole. In this particular problem, instead of having you convert the R to joules, they've converted the delta G to joules for you. You can use it this way. You can use the kilojoules per mole method. I don't care either way. Just make sure you're consistent. If you're using kilojoules, use kilojoules with the R. If you're using joules with the delta G, use joules with the R. So that being said, we're going to use that K equation to figure out what this should be. Now, in K, in general, one of the things that it's showing you is how K changes with temperature. What we should see it doing is going down, right? So these values get smaller and smaller and smaller as we increase our temperature. So when we calculate what we were going to calculate, our value should be below this one, right? We're going to use 298 Kelvin. Our value should be lower than that one. All right. And I think we actually end up getting the 4.34 times 10 to the negative third. So when you're doing this process, make sure you're plugging and checking the right numbers. Okay. The one you're going to do is actually this one. So one of the things you have to do is use the appendix in Appendix C to calculate delta G naught. Okay, so you're going to do the delta G of the products minus the delta G of the reactants to get delta G naught, standard for this reaction at 298 Kelvin. Then you're going to calculate K, by taking the negative delta G naught over R times T. Okay, make sure you're doing all of that, and when you're done with your homework, and then you're just going to turn it in at the link that you were sent in this week's plan. Okay, have a great day.